Welcome! Today I am pleased to present a project titled Teaching an Ancient Calendar to a Microscopic AI. In this study, we explore the capabilities of a minimalist one-layer GPT model written entirely in pure-Zig as it attempts to master a centuries-old system. Specifically, we are repurposing migrogpt-zig to learn the deterministic constraints and complex semantic interactions inherent in the Korean four pillars, or Saju. As illustrated in the diagram, Saju is a sophisticated calendrical framework that maps birth time, year, month, day, and hour to specific elemental relationships. By training such a compact AI on these ancient patterns, we aim to better understand the limits and potential of small-scale neural architectures in representing high-level, rule-based systems. Saju serves as the ideal sandbox for MicroGPT, defined by four primary technical advantages. First, it features a fixed-length structure, where every document consists of exactly 8 Hanja characters, fitting perfectly within a minimal block size. Second, the vocabulary is exceptionally small, restricted to only 10 heavenly stems and 12 earthly branches, totaling just 22 unique characters. Third, it offers learnable constraints by encoding rigid calendrical rules, such as sexagenary parity and 5 tiger escape sequences. Fourth, the system provides verifiable output, allowing generated samples to be mathematically validated for correctness, which yields a concrete success signal. These features enable a remarkably lean model footprint of just 15.6 thousand parameters, operating with a single layer, 4 heads, and a 32-dimensional embedding. By transitioning from byte-level to code point-level processing, we have effectively escaped a major computational bottleneck. Previously, as illustrated in the top panel, a single character had to be decomposed into multiple UTF-8 bytes, such as 0xE5, 0xA3, and 0xAC. This byte-level recombination was computationally expensive and inflated sequence lengths. By moving to a code point-level approach, we can now represent each character as a single token. This change has halved the size of our computation graph from 300,000 to 150,000 nodes and reduced our vocabulary from 36 to 23. As a result, sequence lengths have dropped from 24 tokens down to just 8. Most importantly, this architectural shift allows the model's capacity to be entirely redirected from low-level byte reconstruction to focusing on the actual structure of Saju, significantly improving overall efficiency and performance. The hidden architecture of 4 pillars reveals a deterministic framework underlying the BOSI system. At the top, we see the heavenly stems, which are linked through 2 fundamental predictive rules. The 5 tiger escape ensures that the year stem dictates the month stem, while the 5 rat escape reveals how the day stem determines the hour stem. Moving vertically, the law of parity creates a rigid structure where yang stems only pair with yang branches and yin stems only pair with yin branches. Finally, along the bottom row, the earthly branches follow a fixed orbit, meaning the month and hour branches adhere to a set astronomical ordering. Together, these relationships form a cohesive and mathematically consistent map of time. While our training loss successfully converged to approximately 1.76, generated sequences still require a layer of strict verification to ensure structural perfection. To achieve this, we implemented a rejection sampling pipeline. As shown in the workflow diagram, every sequence generated by the model undergoes a validation process to check against specific parity and rule sets. Currently, our base model achieves an impressive 85% first attempt acceptance rate. The remaining 15% of sequences that fail validation are rejected and sent back to the generation stage. It is important to note that these rare rejections were exclusively due to complex cross-pillar 5-tiger violations. This level of specificity proves that the model has successfully internalized parity and local rules, with the constrained sampling process serving as a final guarantee of reality in the output. Moving from a proof of concept to a functional tool, we have evolved the model beyond simple unconditional generation. While unconditional generation produces random, valid sets of pillars, the implementation of prefix mode enables conditional generation, effectively turning the model into a completion engine. The underlying mechanic involves running a forward pass on forced prefix tokens to warm up the key value cache, before switching to autoregressive sampling for the remainder of the sequence. This is demonstrated in the interface mockup. When a user provides a specific year pillar, such as Ren Shen, the model accepts it as a forced prefix and then generates the month, day, and hour pillars autoregressively. This approach is highly reliable, achieving a 95% validity rate when working with provided prefixes. To introduce semantic meaning into our model, we leverage the framework of the 5 elements: wood, fire, earth, metal, and water. We augmented the training data with deterministic element annotations appended after a separator character. As shown in the diagram, each sequence consists of 8 Hanja pillars, a vertical bar separator, and 8 corresponding element annotations. To accommodate this additional semantic layer, we increased the block size to 24 and expanded the vocabulary to 29. This structure allows the model to explicitly process the relationship between the Hanja characters and their respective elemental properties. Adding explicit element labels created a significant multitask learning effect, allowing the model to perfectly internalize the deterministic pillar-to-element mapping through co-occurrence. As illustrated in the graph, the introduction of element annotations at training step 500, referenced as ADR0005, resulted in a sharp decline in per-token loss. The loss dropped from 1.76 to 0.88, achieving a remarkable 2-fold reduction. Most notably, this improvement was realized without any degradation to the 95% Saju structural validity rate, which remains stable at 95%. Saju's most significant real-world application is gunghop, or compatibility reading. To refine this traditional practice for modern use, we algorithmically scored over 452,904 unique combinations to train our model on the nuances of relationship harmony. The model evaluates 3 core dimensions between person A and person B. First is day-master harmony, which assesses the dynamics of generating and controlling elements. Second is branch interactions, where we analyze specific structural relationships such as the 3 harmonies and 6 harmonies, as well as potential clashes and harms. Finally, we look at overall element balance to ensure mutual support and a lack of elemental extremes. By synthesizing these factors, we can provide a data-driven assessment of interpersonal compatibility. To train the gunghop classifier, we utilized a dataset of 30,000 sampled pairs. We added specific Hangul labels to the vocabulary to facilitate the classification of relational harmony. The input structure for the model consists of 8 character features for person A and 8 for person B, paired with a single target label. We have categorized these outcomes into 3 levels based on their harmony scores. The good category, or Sung, applies to scores of 12 or higher and makes up 34.5% of our data. The moderate category, or Jung, covers scores between 2 and 12, accounting for 36.1%. Finally, the poor category, or Ha, represents scores below 2 and constitutes 29.4%. Moving to gunghop performance and model limits, we observe a stark contrast between classification and generation capabilities. On the classification side, the model achieves perfect success. When operating via prefix completion, it demonstrates flawless format adherence, accurately reading 17 known characters to predict the correct Hangul compatibility label. However, generation presents a significant challenge. When tasked with creating sequences from scratch, only 5% achieve full dual-pillar validity. This limitation stems from the model's architecture. Being a tiny, single-layer, 32-dimensional model, it simply lacks the computational capacity to simultaneously handle the joint probability of 2 perfectly valid interacting pillar sets. The evolution of the astrological engine centers on transforming a basic rule learner into a comprehensive, explainable AI through deliberate capacity increases. By bumping the technical specifications to 2 layers or an embedding size of 64, we lay the groundwork for more advanced functionality. This increased capacity facilitates the generation of detailed readouts, providing users with multi-line, explainable interpretations. Building upon this, the engine incorporates 10 gods analysis to map deeper pillar-to-day master relationships, adding a layer of sophisticated astrological nuance. The roadmap culminates in the production of Dayun timelines, which generate 10-year luck cycles to provide a long-term perspective on personal trajectories.